Welcome to this course Applied Thermodynamics. So, in this course we are in the module 3, that is internal combustion engine. In this module we are going to cover the following topics: internal combustion engines, components, nomenclature, classifications. Second lecture would be basic engine cycle, engine kinematic analysis, engine operating characteristics, thermodynamic analysis of air standard cycles. Then next we have valve timing diagram and fuel air cycle, thermochemistry and fuel characteristics, combustion phenomena in engines, heat transfer analysis in engines. Then finally, we will have exergy analysis, engine pollution and emissions. So, let us start the first lecture. In this first lecture, we are going to discuss about engine components, nomenclatures and classifications. So, let us start what is the engine. In a layman's sense, what we can say is that engine is a device that transforms one form of energy into another, and in thermodynamic sense we say that energy is available in the form of heat or work. Now, from the engine, when you tell this is a IC engine or internal combustion engines, so we say it is a heat engines. So, when it is a heat engines, it converts the chemical energy of a fuel into the mechanical energy in the form of rotating output shaft. So, in thermodynamic sense, we view the output energy as work output in the form of rotating an output shaft. Now, when you do this change from chemical energy to mechanical energy, in the first process what happens, the chemical energy is converted to thermal energy. That means, the energy is available in the form of fuel and it converts to thermal energy, and this happens by the phenomena called as combustions, and this combustion rises the temperature and pressure of the gas within the engine. So, by virtue of this increase pressure and temperatures, when you expand this high pressure gas through some mechanical mechanisms, and in this case we call it as the engine, then we can drive a rotating crankshaft. So, in this process we get the power output in the form of work. Now, the concept of engines comes from the fundamental second law of thermodynamics, and it is governed through Carnot cycle. So, in this Carnot cycles, what we have is, if you look at this figure, we have a source, we have a sink, and between the source and sink there is a cyclic device. So, this particular circular one we call this as a cyclic device. So, in this cyclic device what happens, it receives the heat from the source, and this heat comes from fuel and air mixtures in the form of Q1, and finally it is combusted in this cyclic device, and after combustions we get work output in the form of the rotating crankshaft, and the exhaust energy, or we call this as waste heat, goes to the sink. So, the second law of thermodynamics, that is Carnot cycle, is the governing principle for IC engine operation. Now, let us see that in what sense we can classify these heat engines. So, normally heat engines are classified as internal combustion engines and external combustion engines. So, in an external combustion engine, the combustion mostly takes place at the outside of the mechanical systems. So, for example, in this Carnot cycle, if you just suppress this as one particular part and you say this is source is a location where we can say we can burn the fuel and air through combustion, and this particular part we isolate it from the rest of the components, then we can say that the combustion takes place outside the mechanical engineering components. So, these particular things we call this as a external combustion engines. Typically, one particular example what we can give is that in a boiler. The boiler in a steam power plant receives fuel and air mixture, and somewhere outside this boiler the heat takes place, and that heat is used to change the state of water to steam, and finally the combustion products goes out. So, this particular part we say these are EC, external combustion engine, but that is not part of this particular module. We will be mostly concentrate on the internal combustion engine part. So, that we view in this Carnot cycle in this format. So, where heat is added to the engine. So, we say IC engine in the form of fuel and air, and through this after the combustion within the engines we get shaft output in the form of work at the and rest of the combustion products goes out to the sink, and this is atmosphere. And our main focus will be on this part. Now, the question here is that this engine can be of reciprocating type or rotary type. So, this IC engine can be of reciprocating type or rotary type, and in our analysis we will mostly consider on the reciprocating type engine. Now, to give some of the more insight to these engines, when in the process of this Carnot cycle, when you take the power output, two ways in we can view this output, or in there are multiple ways that you can use this power output. So, one particular sense that we can take this as a electric power or power output. Other way is that you take this work output in the form of creating propulsion or motion of a particular body. So, that things we call are mainly used in the transport sector, where power is transmitted in moving a vehicle. So, in that sense we use this power as a propulsion device. So, in some sense also automobile it is a moving vehicle, locomotives, marine vessels, airplanes, all these cases it is moving a particular vehicle. But there are other usages as well. So, we can think of even a stationary engines in the form of generator or pumps that are also used, but they are not in the most moving any type of vehicle or body, rather they are used mainly for transmitting power. Now, when you say reciprocating engines, there are possibilities that we can have single cylinder, multi cylinders, and they can range from different powers from 100 watt to thousands of kilowatt per cylinders. Now, in this particular things, there are many manufacturers that they produce IC engines. So, those engines can vary in size, geometry, style, operating characteristics, etc. However, our main focus in this IC engine will be mainly thermodynamics parts, because the course theme is applied thermodynamics, and for IC engines applications we are tried to focus how we can link its fundamental principle with respect to thermodynamic laws. To give certain background to this engine development, I have listed down some of the concepts which were in existence since 17th and 18th century. During that time when the engine comes to the existence, it was called as atmospheric engines, where atmosphere and vacuum were treated as the two pressure differentials to run that engines. Slowly in the 20th century, the petroleum industries started producing fuel. So, otherwise because the engine requires some fuel, so petroleum industry started producing fuels, and through this process of developments we have development of rubber tires for the motion of the vehicle, The first practical engine was realized, or maybe you can say commercial version was realized by Lionier sometimes in the 19th century, and those fundamental principle of those developments was based on two concepts. One is SI engine concept, which is called as spark ignition, other was the compression engine concept, that is SCI engines. And in fact, all of us were familiar that those engine developments were developed by Nicholas A. Otto. So, based on which we have Otto cycle, and R. Diesel, based on which we have diesel cycles. And to many a times what happens, to run this engine or to start the engines, we require some initial thrust. So, for which an electrical mechanisms in the form of electrical starter was developed in the year 1912. So, for the starting purpose we require some electric mechanism to start the automobiles. But till this point of time IC engines have been used in plenty, but however, in the 21st century the IC engines role is going to be obsolete because of the scarcity of the fuel, and what is coming to the market, they are named as electric propulsion system or electric vehicles. So, now let me start the basic engine components. So, in this basic engine components, what I have shown here is a typical cross section of an engine block or engine arrangement, in which there are many components that is integrated to make a complete engine setup. So, the first component is the engine block. So, it is the body of the engine containing cylinders made out of cast iron or aluminum, and it houses all the supporting structures. The next important item is the cylinder and pistons. So, in the cylinder and piston, what you see in this figure is, this is the piston and this is housed within a cylinder, and these are two are the integral part of the engines. And if you see with piston, piston has one upper part which is called as crown, we have side part which is called as skirt, and the piston movement within the cylinder has to be smooth. So, for that reason there are piston rings that are housed in the circumferences. So, this allows the smooth motion of the piston within the cylinders. So, this is how what I have written here. This cylinder and piston are the integral part of the engines. Piston is the cylindrical shaped mass that reciprocates back and forth within the cylinder. The top part of the piston is called as crown, where the sides are called as skirts. Piston is made out of cast iron, steel or aluminum, and there are piston rings that are kept in the circumferential grooves around the pistons, and it forms the sliding surfaces against the cylinder wall. Now, the motion of this piston, which is linear in nature, has to be converted to rotary motion. In rotary motion, so that we can get that rotary motion in the form of rotating crankshaft. To do that, the piston is connected to the crankshaft through a connecting rod. So, the connecting rod interconnects the piston of the engine to the crankshaft for transmitting gas force from the piston to the crankshaft. Now, in order to connect these two things, one we have a gudgeon pin. Gudgeon pin means this connecting rod has two parts, one is big end and other is small end. The small end is connected to the piston and through a gudgeon pin, whereas big end of the connecting rod is connected to the piston through crank pin. Then we have a crankshaft, because this crank pin and the crankshaft, they are integral part. So, when we have, then the crankshaft converts the reciprocating motion of the piston to the rotary motion of the shaft output. So, how it does we will see in the later part of this course. Then we have crankcase, it is the part of the engine block that surrounds the rotating crankshaft. The next important segments of this engine is the camshaft. What we require is that we require fuel into the engines, that has to come, and also we require air into the intake system to the engines. So, all these things come from to the engines through an intake manifold, but what happens is that the engine requires fuel and air in proper timing and for certain durations, and also the fuel also be ignited at right time. So, entire things is governed through a shaft, what we call as a camshaft. So, this camshaft allows or regulates the inlet and exhaust valves for correct timings and keep them open for certain durations. So, it provides a drive for the ignition systems. Now, from when the air fuel mixture goes into the combustion chamber. So, this is what we have in next important component, which is the combustion chamber. It is the space enclosed in the upper part of the cylinder. The combustion of fuel and consequent release of energy builds up pressure in these regions. So, typically the size of the combustion chamber changes from minimum value to the maximum value. The size or space means the amount or slug of mass that gets accumulated within the chamber, that changes because of the piston movement. So, the minimum volume is acquired when the piston is at TDC, maximum value is acquired when the piston is at BDC. Also, I explained that there are intake and exhaust manifold. These are the connecting pipes with lot of valves in between that regulates the air and fuel to come into this engine, and also at the same time the exhaust manifold will allow the all unwanted combustion products to go out of the engines. So, apart from these basic components, there are many other components. I can just spell out some of them, that we have a carburetor. So, it is nothing but a Venturi type flow device that controls the air flow rate to the SI engine. In fact, this is carburetor is main component for an SI engines, and essentially this gives a pressure difference, so that the intake air enters into the engine. Now, in this SI engines there is another mechanism in which the fuel needs to be ignited. So that combustion process can be initiated. So, that is done forcibly by a spark plug or through an electric discharge created at a particular time. There is another component which is called a choke or throttle. This particular choke or throttle we used to have very common practices in our day to day life while driving a two wheelers or any bike. So, it is nothing but it is a butterfly valve that creates a fuel rich mixture into the intake systems. It allows more fuel to enter into the engines from the fuel tank. And also this is, and for in particular there are other devices like fuel injector. So, these are kind of pressurized nozzles that sprays fuel into the incoming air for SI engines and into the cylinder in a CI engines. So, directly it is sprayed into the cylinder for CI engines. So, we have fuel pump. So, it is an electrical or mechanically driven pump to supply fuel from the fuel tank to the engines. Then we also have oil pump. So, oil pump is something like it is like a lubricating oil. So, it has nothing to do with the fuel system, it has a lubricating oil. As I mentioned that there are many mechanical components that needs to be lubricated properly. For example, when the piston moves within the cylinder, there are piston rings and there are some space in which the lubricating oils also has to be pumped in, because we expect the piston movement is smooth within the cylinders. So, for that reason we call this as a oil pump, and in typically we say lubricating oil pump. It distributes oil from oil sump to the lubricating points. There are also water pumps. And this water pump is mainly used for CI engines, because we require some engine coolant that needs to be circulated to take away heat from the engines. Also and if there is no water pump, we can have also radiator, and radiator also there are radiators that needs to be also cooled. There are also we have water jackets, that means in a big engines we use some kind of liquid flow passages that surrounds the cylinders and structured as a part of the engine blocks. So, you can provide it is like a sweater for the engines, and that here the idea of this, that jacket takes away all kind of heat, water jacket takes away heat from the engine cylinder. In small engines we have radiators, they are in the form of fins. So, it is a liquid to air heat exchanger that removes heat from the engine coolant. Apart from this, there we have flywheels. So, these are inertial mass in the form of wheel attached to the output shaft to achieve uniform torque or power. So, what happens, since it is a reciprocating engines, there is one particular cycle there is a power, the rest of the cycles there is no power. But ideally the body or vehicle has to move at uniform speeds. This entire thing is governed through a mechanism called as flywheel. So, these are all the basic components for any normal engines, but in advanced engines people think of additional components, and first additional components is a supercharger. So, what it does is that it gives additional increase in the pressure apart from its normal value. So, this is done through a mechanical compressors, and basically speaking, if you look at this particular figure, we have the air intake system to the engines. So, this particular part the fuel has to come, or air fuel has to come to this combustion chamber, and ideally for a normal engines the passage, the fuel and air mixture or air mixture or only air that has to come to this engines in a normal engine. But what happens in a supercharged engines, this particular movement of air is again is controlled through a mechanical compressors which is housed here. So, instead of directly sending into the engine cylinder, it has to go through these compressors as a for additional pressure boost. So, these particular compressors, what it does, it gives a additional inlet air pressure to the engines. So, normally we refer this as a pressure augmentation. So, in this process what advantage we get is that it provides the fast response to the engine speed changes. That means, whenever we change the speed of the engine, immediately it responds, because we have a supercharger. But the main drawback is that it is added as a parasitic load to the engines, means that it needs to be powered from the main engine systems. So, the compressor is driven through the engine crankshaft, because it takes the power from the main engine itself. Now, there are other concept as well. So, we have the turbocharger. So, the turbocharger it is also does the same thing, that it gives a pressure augmentations or it increases inlet air pressure of the engines, but through a different technology. What is that? That is called as turbine compressor assembly. And through this turbine compressor assembly, it performs one important role, that in terms of thermodynamic sense, waste heat recovery. So, from the engine exhaust we can say that a lot of unwanted energies are still available, but we can use them with proper arrangements. So, a mechanism is thought of in which the turbine is used and it is powered through the exhaust flow of the engines, and these turbines drives the compressor, in a sense that the turbine does not take any extra power from the main engine block, rather it taps the heat or energy from the exhaust gas and that runs the compressors. So, it does not add extra power to the engines. So, that is main difference between a turbocharger or supercharger. But what happens to the things that when we run these turbocharged engines, there is a kind of a lag. So, when the user changes the engine speed, there is a lag, what we call as turbo lag or slower response, but it adds pressure augmentation, but at a relatively slower response. So, we call this as a turbo lag. So, that is the main difference between a turbocharger and supercharger. Then we will move to the next segment of this particular lecture, that is engine nomenclatures. So, I have mentioned that cylinder and pistons, these are two important segments of any IC engine, and here it is represented in a very schematic manner, and in fact what we have shown is that the complicated structure of an engine can be represented by these simple geometric dimensions. What we see here, we have a piston, and this is the crankshaft, and this part we say it is a connecting rod, and the piston is connected to this crankshaft through this connecting rod. But what we are at this point of time we will discuss is that some important terms with respect to engines. First important term is engine bore. So, engine bore is nothing but the inner diameter of the cylinder, which is slightly higher than that of piston. So, basically the piston and cylinder dimension are adjusted with a very little bit tolerance, so that piston can move smoothly within the cylinders. Typically, the bore diameter is in the range of 0.5 mm to 0.5 meter. So, once we have engine bore and the cross section is circular, so you can have the piston area, that is the area of circle diameter equal to the cylinder bore. Then we have stroke, that is nominal distance through which the piston moves between two successive reversal of its motions. So, what it means is that piston moves the cylinder back and forth. There is a upper position which is called a TDC, top dead center, that is the upper limit in which piston can go within the cylinder. The bottom limit the piston can go is up to is BDC. So, distance between the TDC and BDC, we call this as a stroke, and in fact from TDC the piston reverses its path. So, we call this as a reversal of its motion, and same thing happens at BDC, the piston reverses its path from bottom to top. And now we have also another term which is called as B by S ratio, that is bore to stroke ratio. So, it is one of the specification of the engines, and for any normal engines its value is in the range of 0.8 to 1.2. In this terminology we can have a larger bore, shorter stroke, or shorter stroke, larger bore. So, based on that B by S ratio tells you that whether an engine is over square, or that is B by S greater than 1, whether it is under square, B by S less than 1, and it is equal to 1, that is square engine. Also I mentioned the word dead centers, and it is the position of the working piston and the moving part at two instances. One is when there is a reversal in the piston directions. So, one we call this as a top dead center TDC, other you call as bottom dead center BDC. So, these are the terminology which we will be using frequently. The next important term what we are going to use is the displacement or stroke volume. So, once we have all the dimensions of bore and stroke, then we can express them in the form of volume, because volume is required because the slug of mass is contained within a certain space. So, the displacement or stroke volume is defined as the nominal volume swept by the piston when it travels from one dead center to other dead center. And typically most of the engine cylinders are specified in the form of cc, 100 cc, 1000 cc, 800 cc. So, this cc means we refer as cubic centimeters. So, all these numbers what we call as a stroke volume. Next we have the clearance volume. So, what happens is that when the piston is at TDC, there is some kind of a volume which is remains as a clearance volume, and this is required because this has a very significant impact in the combustion chamber, because entire volume has to be squeezed in a particular space during the engine operations. So, we call this as a clearance volume. So, it is the nominal volume of the combustion chamber above the piston when it is at TDC. So, when the piston is at TDC, the volume which is how enclosed in this combustion chamber. So, we call this as a clearance volume. So, here it is represented as a VC. Then we have engine capacity. So, engine capacity means in this case we have one cylinder, one piston. In a particular engine we can have a multiple cylinders, multiple number of pistons. So, engine capacity is nothing but it is the displaced volume of an engine cylinders multiplied by number of engine cylinders. Then another important word that we mainly use in this IC engine terminology, which is called as compression ratio. So, it is the ratio of the total cylinder volume when the piston is at BDC to the clearance volume. So, whatever I have explained here, mathematically we can represent Vs is nothing but the stroke volume, that is nothing but area of the piston into stroke, that is nothing but pi by 4 B square into S. So, if there are k number of cylinders, then total engine capacity would be VE, that is equal to k times Vs. Now, based on the definition of compression ratio, we can write the compression ratio is the total volume to the clearance volume. Total volume constitutes two parts, one is stroke volume plus clearance volume divided by clearance volume, and finally, compression ratio mathematically is represented Cr is equal to 1 plus Bs by Bc. Then we talk about something about classification of the engines. So, in the classification of the engines, we are going to discuss in some sense. One is the nature of ignitions. So, nature of ignition means that when the combustion has to be initiated within the engine cylinders, there are two ways where one can do. One is manually create an ignitions, other way is that we allow the charge to ignite spontaneously on its own. So, based on that we call this as a spark ignition engines or ignition engines. So, when the fuel and air combustion process in the engine is initiated with a very high voltage discharge by using a spark plug. So, we call this as a spark ignition engines. When this fuel air mixture is self ignited due to high temperatures or due to compression on its own, then we call this as a compression ignition engines. In the form of engine cycle, one can differentiate the engines as a 2-stroke engine cycle or 4-stroke engine cycles. So, when there is a 4 piston movement for 2 engine revolution in each cycles, or in other words, we obtain 1 power strokes per 2 crank revolution, then we call this as a 4-stroke engines. 1 power stroke is obtained per 2 crankshaft revolutions. But in a 2-stroke engines, there are 2 piston movements over 1 engine revolution cycles. So, we get 1 power stroke per crankshaft revolutions. So, in the bottom line we say that 1 power stroke per 2 crankshaft revolution in a 4-stroke engine and 1 power stroke per crankshaft revolution in a 2-stroke engines. I will be explaining in details in subsequent lectures. And in the basic designs, that the engine can be of reciprocating nature or we can have rotating in natures. So, in a reciprocating nature we have seen that the piston moves back and forth and there could be in one or multiple number of cylinders. So, the nature of the motion is reciprocating in nature. But in a complicated motion or in the rotary engines which are typically used in the turbo machines and aircraft engines, where they are used as rotary engines, where they have starter blocks and with non-concentric rotor. So, those rotary engines are used mainly for aircraft applications. But however, a commercial application for a rotary engine which was built, we call this as a Wankel engine. Wankel engine a very common engine in a Mazda model. So, their design in automobile sector comes under rotary engine category. The other classification goes in the form of engine geometry, where the location of the valve. So, based on the engine geometry, many manufacturers try to optimize their engine shape designs in such a way they can get they can improve the engines with a larger run or operations. So, for that there are many designs are possible. One can think of L heads. So, L heads means that is valve on the bulb, that means the inlet or exit valve which is kept in the engine block. So, it is a flat head or L head engines. This valve can be directly kept on the head itself. So, it is a I head engine. When there are inlet and exit valve, one can think of one valve on the head and other valve on the block. So, this can be a possible combinations, that means we can think of one as inlet valve, other may be exit valve. So, this particular design we call this as a F head engine. There are other possibilities that we have engine cylinders, we have head and the valves are located on either side of the cylinders. So, it represents a shape of T. So, it is a T head engines. So, there are in that way there are multiple number of designs that are possible. Another way of looking the classification is that how the pistons and cylinders are oriented. So, in a single cylinder engines we have one cylinder and one pistons, or we can have one single straight cylinder, there may be multiple number of pistons. We can have a V engines where there are multiple cylinders and multiple piston, each cylinder and each cylinder has its own pistons, but they have made some angle which is in the range of 60 to 90 degrees, and when two such V engines are joined together we get a W engines or two V8 engines are connected to a single crankshaft. Then we have a concept of opposed piston engine, that means where the combustion chamber is kept at the center between the pistons. Then we have upper cylinder engines. Also we have can have radial engines. So, these are the engines with piston positioned in a circular plane around the central crankshaft. We have a central crankshaft, but the pistons are uniformly distributed radially. So, these are called radial engines. So, based on these kind of arrangements, the automobile manufacturers use their concept for improving the performance of the engines. Then the classification goes in other direction as well in air intake process. So, the engine requires fuel and air, and this air intake, now if you talk the engine with respect to air intake, how air enters into the cylinder, there are possible ways that we can in a normal aspirated engines, that means in a normal engines where there is no boosting of air, it comes on its own through air intake or air manifold. So, it is a naturally aspirated engines. I also mentioned the supercharged engine and turbocharged engines in which intake air pressure is increased with compressions. So, these are the two integral parts in which the intake air pressure boost up, and typically these are the part of the 4-stroke engines, and these supercharged or turbocharged engines are modular in nature. So, they can be integrated to any naturally aspirated engines. But when we have a 2-stroke, there is on the concept of there is a crankcase compressed engines. So, these particular engines were used for 2-stroke cycles, in which they use compressors for intake air boosting. So, by default in a 2-stroke engine cycle there was a compressor within the crankcase. So, we say crankcase compressed engines. So, in fact, since there is no 2-stroke engines in the market, so this concept is now obsolete. Now, based on the fuel usage, engines can use liquid fuels, mostly liquid fuels, or it can you run the engine with solid fuel as well. So, accordingly we have a gasoline or diesel engines which are conventional liquid fuels. We have methyl and ethyl alcohols, bio oils, these are alternative liquid fuels. We can have compressed natural gas and liquefied petroleum gas, and in the advanced developments people are thinking of using methane and hydrogen as the fuel usage, and there are other research concept that goes as a dual fuel engines in which both liquid as well as gaseous fuels can be used simultaneously in an engine. So, those engines are called as dual fuel engines. And the last few concept is that fuel input method. So, we said that how air comes to the engine, now we will say how fuel comes to the engines. So, basically there could be two possibilities, one we can use for SI engines, other could be used for CI engines. So, a basic difference is that in a SI engines fuel and air mixture enters into the combustion chamber as a well. So, when they enter they are to be mixed properly. So, we say it is a carbureted engines, and these air fuel mixtures can go as a multi-point port fuel injection mode. That means, there are one or fuel injector at the intake, or we can take the entire slug go as a single entity. So, we call it as a throttle body fuel injection. That means, injectors are in the we can have to, in that case we have to use the injector in the intake manifold. The other option or most efficient option could be we can use this as a direct injection mode into the combustion chamber directly. So, this is how we can inject the fuel in an SI engines. In a CI engines the concept goes in a different way, air is compressed in the cylinder, fuel is injected into the cylinder directly. So, the possibilities could be that we have to inject, we have to use fuel nozzles for direct injection of the fuel into the main combustion chamber. Other possibility is that if there are big engines and there are provisions, then we can think of a secondary combustion chambers. That means, we can have a main combustion chamber, we can have a secondary combustion chamber. So, where indirect injection is also possible. And in advanced technology people think of homogeneous charge compression ignition engines. That means, fuels are added during intake stroke. Ideally in the intake stroke we only compress the air, but here what we say that people think of that during intake stroke itself one can think of injecting the fuel into the cylinder. And based on the type of cooling, so we have seen that the engine exhaust in the form of combustion products. So, most of the heat goes as a waste. So, to do that and in fact the engine gets hot and hot as and when it operates. So, based on that we can have a air cooled engines, typically SI engines where the engine is cooled by means of circulating air. Other option is that we can think of liquid water cooled engines, or we can think of water jackets. So, that is mainly used for CI engines. And lastly, with respect to application point of view, we can use these engines either in the automobile sector, locomotive sector, agricultural sector, marines and aircrafts. So, these are the classifications of engines in variety segments. So, with this I conclude this first lecture, but before I make the final things, let us see what we have studied so far. Just to refresh some of our study or analysis, we try to solve some numerical problems. The first problem is that which is given to us is that there is a 4-cylinder SI engines and it is designed for a compression ratio of 8, and given that it has a swept volume of 0.20028 meter cube, and it is a square engines So, we have to calculate the bore, stroke and clearance volume of the engines. So, to start with, we can say that what are the data is given to us. So, let us solve this problem. So, it is a square engine. So, you can say the bore and stroke are equal, that is for square engine. Swept volume is given as V s, which is nothing but pi by 4 B square S, and 0.0028. And this swept volume, what we have said is that it is for 4 cylinders. So, for 4 cylinder means that we can say this pi by 4 B square S into 4 would be equal to 0.0028. Since the 4 gets cancelled, so we say pi by 4 B q, because S is equal to B, is equal to 0.0028. So, by solving we can get B would be 0.0028 by pi by 4. 4 gets cancelled means it will be pi into B q by pi to the power 1 by 3. So, this turns out to be 96 mm. So, since B is equal to S, so S would be 96 mm. So, once you know B and S, so you got B, stroke, then and clearance volume. To get this clearance volume, we require compression ratio. So, compression ratio CR can be written as 1 plus Vs by Vc. So, putting and from this we can get 8 is equal to 1 plus 0.0028 by 4, because there are 4 cylinders, divided by Vc. By solving them we can get clearance volume would be 0.001 meter cube. So, we get all the answers. So, based on this particular geometry, we can say we have this clearance volume to be 0.001 meter cube. So, this particular problem was given for square engines. There is another similar problem in this direction, that is over square engines, where there is a definite ratio between B by S. So, for an over square engines, we say B by S is equal to 1.1. So, and it is, of course, there is no mention about number of cylinders. So, you take the entire thing as Vs, and from this B by S we can get S is equal to B by 1.1. So, we are also given Vc as 27.2 cc. Cc means I can write 27.2 centimeter cube, and Vs would be 245 cc. Then from this what we can say, we will recall our first fundamental principle, that is pi by 4 B square S is equal to 245, and from this S will be B by 1.1 is equal to 245. From this we can get B as 6.98 centimeter. Closely we can approximate as 7 centimeters. So, since we know B, so A should be B by 1.1, that is 7 by 1.1. This number turns out to be 6.36 centimeter. So, we know we got bore, we got stroke. So, by definition of compression ratio, we can write CR is equal to 1 plus BS by BC or BS plus BC by BC. So, all these numbers are given, that is 245 plus 27 point divided by 27.2. So, CR turns out to be 10. So, we got all the answers: bore, stroke and compression ratio. So, these are the two small problems which will refresh our concepts. So, with this I conclude my talk for this lectures. Thank you for your attention.